Today we're going to be introducing spheres and talking about how to find the volume of spheres. And in order to help us, we are going to revisit all of the other ways in which we use pi as a constant of proportionality in finding one-dimensional, two-dimensional, and now three-dimensional space. So for starters, it's important to understand that there is always a proportional relationship between circular measurements and dimensional measurements. Now, when I say dimensional measurements, I am referring to ones that are regular. So if we're talking about one-dimensional, we're talking about stuff you can measure with a ruler or a meter stick, a single dimension length. However, if we're talking about two dimensions, then we're talking about a square, because a square is the basic unit of area. If we're talking about volume, then we're talking about a cube. A cube is the basic unit of volume. So when we say we're talking about the constant proportionality between a dimensional measurement and a circular measurement, we are talking, therefore, about length versus circumference, square area versus circular area, and cubic volume versus sphere volume. Or I should say cube volume versus sphere volume. The constant proportionality for converting dimensional measurements into circular ones is always a multiple or a fraction of pi. And learning which ones go with which formula, and also why they go with the formulas they go to, will go a long way towards helping us to memorize, understand, and use the various formulas that we do. So for starters, there are two different measurements, one-dimensional measurements we can take of a circle. We can either get the radius, which is the distance from the center to the edge of the circle, or we can get the diameter, which is the distance from one edge of the circle to the opposite edge through the center. As you should already know, a diameter is twice as long as a radius, and the formulas reflect that. The constant of proportionality between a diameter and circumference is simply 1 pi. Whereas if we're going from a radius, the constant of proportionality is 2 pi. That extra 2 is accounting for the fact that the radius is half the length, and therefore you need to multiply by twice as much. Simple enough so far. And then as you recall, when we're trying to find circular area, we are basing it off of a square area. So we could start with a diameter square, which encompasses the entire circle, or we can start with a smaller radius square. Now, the first thing I want you to see is the relationship between the diameter square and the radius square. If we were to overlay a radius square on a diameter square, it would become pretty apparent very quickly that it would take 4 radius squares in order to equal 1 diameter square. So understanding that the diameter square is 4 times the area of the radius square, it then puts these formulas in perspective. For the radius square, the constant proportionality is simply pi. Whereas for the diameter square, it's only 1/4 of pi. And that accounts for the fact that the diameter square is 4 times as large as the radius square. I put down here that you could think of the 1 pi for the radius square as actually 4 over 4 pi, accentuating the 4 times as, or I should say 1/4 the size that the radius square is compared to the diameter square. And finally, let's take it into the third dimension with sphere volume. We're going to start with finding a cube volume. Once again, we can start with a diameter cube, or we can start with a radius cube. Now, if we're starting with the diameter cube, which can encompass the entire sphere, the constant proportionality is 1/6 of pi. Therefore, our volume formula could be considered d to the third power times pi divided by 6. Alternatively, if we're starting with a radius cube, the formula is 4 over 3 times the radius cube times pi. Now, 4 over 3 doesn't make all that much sense unless you're willing to perceive it as 8 over 6 pi. Then it becomes apparent that you're taking the 1 over 6 pi from the diameter cube and simply multiplying it by 8. Why are we multiplying it by 8? Well, because the diameter cube is 8 times the volume of the radius cube. So to summarize, circle-related measurements are proportional two-dimensional measurements of the same dimensional degree. So what I'm saying is that we have to consider what dimension we're in. If we're finding a one-dimensional measurement, then the constant proportionality comes from another one-dimensional measurement. However, if we're looking for an area of a circle, then we need to start with an area of a square. Likewise, if we're starting with if we're trying to find the volume of a sphere, we need to start with the volume of a cube. We need to get into the right number of dimensions first, and then we can apply our constant of proportionality, which is always a multiple or fraction of pi, fortunately for us. So let's try a sample problem. A pearl is formed when an oyster covers a grain of sand with mucus, which hardens into the spherical object we like to wear as jewelry. Ew! Here is a picture of a pearl inside of an oyster. And that's exactly how it looks like when they form. Now here's the math problem. If an oyster applies a 2 millimeter thick layer of mucus around the grain of sand, what is the volume of the resulting pearl? Go ahead and give it a try. I'm going to start flipping through the slides. Feel free to pause at any time if you need a hint and want to try the rest on your own. Or just let it play if you want to see the entire thing. So first of all, what formula should we use? We should probably use the one that's based on the radius cube. The reason why we're starting with the radius cube is because the 2 millimeters of thickness is a radius. And we know this because it says that it's around the grain of sand, meaning the grain of sand is at the center. Therefore, if we plug in that 2 millimeters, we're ready to set out to find V. Our first step should be to find out what 2 cubed is, which is 8, and then multiply that by 4/3 and times pi, which gives us 32 over 3 times pi, which we can then approximate using 3.14 into about 33.5 cubic millimeters. Second problem. A basketball with a volume of 121.5 pi cubic inches fits snugly inside a cardboard box. What are the dimensions of the box? Now take note that pi is included in the volume already, which means that when we inevitably have to divide by pi, we're not going to end up with a messy number. We can just divide away the pi. So you're welcome. So the formula we probably want to use is the diameter cube formula, since we are looking for the dimensions of the box. And the dimensions of the box, as we can see, the width and length of this box, since the box goes around the entire ball, those are going to be based on the diameter. Well, they actually will be equal to the diameter, come to think about it. So we can even just draw that. This is going to be equal to the diameter. The width is also going to be equal to the diameter. It's going to be a square box because it's fitting snugly around a sphere. So, since we know the volume already, 121.5 pi, we can set it in for b and then solve for d. The first thing we should do is divide both the pi's away and then also multiply both sides by 6 to try and isolate our d cubed. We should end up with 729, a nice whole number, and a perfect cube, is equal to the diameter cubed. A quick little bit of cube rooting will reveal that our diameter is 9. And therefore, that's the dimensions of our box. A length of 9, a width of 9, and a depth of 9.